Okay, I'm going to see if this works to put sound to a video that I did earlier and the sound did not work. Okay, we'll see how this goes. Right, in this video, I am teaching you how to handle all of the graphing that we did to help understand circular motion and gravitational motion. So right now I just need to wait. Okay, there we go. Sort of. I don't think I'm quite where I needed to be. Okay, I think I'm showing you that on the calendar, if you go to the calendar, you will see the link for the PhET. And the link for the PhET takes you to where you were supposed to take data, right here on the screen. So you take the data with the relationship between force and mass, and also the relationship between force and radius, or distance between the two masses. So then we graphed it. And this is where I graphed the data that I took for force and mass. And it's easy to see that in this relationship, it's linear. And the linear relationship means that as the mass increases, the force also increases. And we can write that in an equation form. And I think I do that pretty soon here in the video. Oh, I do. Here I go. Okay, so force is on the left. And over on the right, we have to put the mass somewhere. And because they are directly related, the mass will just be where it is written. Okay. Now we have to figure out the rest of the relationship because we needed to figure out how the radius, or the distance between the masses, will be affected. We also need to figure out that other mass. And what I'm showing you here is that either mass, when it's being changed, has a linear relationship to force. And it turns out that that means both masses are involved. And it turns out that the two masses are multiplied by each other. Now that's pretty tricky. So I didn't expect you to get that necessarily by itself, but try it. Graph mass 1 times mass 2 and see that you get a linear relationship to the force. Okay. The other thing we had to graph with the PhET was the relationship between the force and the radius. So we did that, and we had a curve. And on that curve, we have to know the relationship. Of course, the relationship is on the cheat sheet, and the cheat sheet tells me that I should graph 1 over x to try to make it linear. And so I do that eventually on this video somewhere. There we go. Okay, so that's where I'm telling you that that's what you're supposed to graph. And now let's see if I actually graph it. Oh, I do. So I'm going to pick it. I'm actually going to auto scale the screen right now so that you can see it. Oh, wait, it's not a line. It's still a curve. And if I look at the cheat sheet, this curve now tells me that, well, maybe I need to graph y versus x squared. So I need to linearize it again. And when I graph the 1 over x squared, I have to graph 1 over radius squared. So I'm showing you on the screen now that you're going to graph force and 1 over the radius quantity squared, which is just 1 over radius squared. Okay, so we graph that, and let's see what happens when we graph that. And we get a linear relationship. Nice linear fit. So that tells me that force has a linear relationship to 1 over r squared. So we already figured out that force has a linear relationship to the mass, so mass 1 times mass 2, and it has a linear relationship to 1 over r squared. So eventually, I think I draw in the r squared here. Oh, good, I did. But now we have a problem because mass 1 times mass 2 divided by r squared, if you go back to the PhET and take the data, it doesn't match. It doesn't match the force. And so we have to figure out why not. And the reason why not is there is a little constant that's missing from the equation. That constant is big G. It's called the universal gravitational constant. I shall pause while I write it down. Okay, that universal gravitational constant has a value of 6.67 times 10 to the negative 11 Newton meters squared over kilograms squared. So now we should go back to the PhET and make sure that we understand how all of these numbers work together. So let's use the example that's on the screen because I think that's what I did earlier. So F is equal to G m1 m2 over r squared. So the G is 6.67 times 10 to the negative 11 Newton meter squared over kilogram squared. And we're going to use the values of mass 1 and mass 2 that are on the screen and the radius that's on the screen. Okay, so mass 1 is 50 kilograms. I'm going to make sure I keep using all the units that will cancel out appropriately. My mass 2 is 200 kilograms. The kilograms will cancel. And that's over r squared, and r squared will be, if I look from center to center, it's 4 meters, so 4 meters squared. Grab your calculator. Well, I grab my calculator and find the value that you have for all those numbers. Okay, and it turns out that we have 7 zeros and then 4 2 on my calculator screen. And if I compare that to what's on the screen for the force, it rounds to be the same number. And of course, that is in newtons. Okay, so now we have shown that this is the equation or the model for gravitational force. And now I'm just waiting on myself. I've got to figure out where I go next. I think I was talking to you about something. Oh, here we go. So now we're going to go through the model. So this is the gravitational force. This is the model. F is equal to G m1 m2 over r squared. And that little g tells me that this is gravitational force. But this is the generic version, if you will. This is the version that works for all masses at all distances. The one that we use for weight here on the surface of the Earth is specific only to objects close to the surface of the Earth. M1 and M2 in this equation are two masses. They are any two masses, big masses, small masses, doesn't matter. They're two masses that are gravitationally attracted to each other. And R is the separation of the centers of those masses. G is the universal gravitational constant, which we wrote down before, 6.67 times 10 to the negative 11 Newton meters squared over kilogram squared. Okay, so now we have a model for gravitational force. And we are ready to look at what we did with the pivot interactives. Okay, on the pivot interactives, let's go back. I'm scrolling up to show you some information about the data collection screen. On the data collection screen, it's really important that you select your independent variable and then also select the values for your constants. So in this case, I was selecting mass as the independent variable, and then I selected radius b and speed 2. And then I hit go. If I don't hit go, then it doesn't set the device to actually show me the correct data. So I would have trouble. So make sure I hit go, and then I'm ready to take the data. Okay, so the first thing I did was I took data for mass and force. And I found that when I graphed it, I got a linear relationship, which is great. We know what to do with it. And it turns out that I think I'm going to show you here in just a second that with a linear relationship, I'll just wait on myself. Okay, so force is equal to something on the other side. And it turns out that the mass is directly related, so we're going to put the m right there. Now that looks very suspiciously like something we already know, which is Newton's second law. And if we look at the units, just in case we're wondering, it's Newton's over kilograms for the slope. And what I get for the slope is, oh look, units of acceleration. So it turns out that, yeah, that equation must just be F equals ma. But since it's centripetal force, since that's the force making it go in the circle, in this case the tension is the centripetal force, we're going to say centripetal force is equal to mass times centripetal acceleration, since that is the net force and the net acceleration. So we're going to be figuring out acceleration as we do look at the rest of this data. Okay, let's go on to the next thing that we took data for. And we took data for radius and force. Now, the first thing I graphed was force on the y and radius on the x. And I got a curve. And that curve told me that maybe it's linear if I graph 1 over x. So then I tried 1 over the radius. And I got a nice straight line. So that tells me force has a linear relationship with 1 over the radius. And that means on the right-hand side of that equation, somewhere I have 1 over the radius. If I want to combine that with what I figured out already about the mass, I end up with something on the right is mass over radius. And now we need to investigate the third relationship to see if we can put it all together. Okay, so the third relationship was speed and force. And I got a curve, and the curve seems to indicate that we should graph y and x squared. So that's what I did. And it turns out I get a linear relationship. So that means force has a linear relationship with speed squared. So somewhere on the right side of that equation is v squared. And we understand that in circular motion, the v really only means the magnitude or the speed of the velocity, since the direction is always changing. And we can put that all together with what we've learned, and it's mv squared over r. There are no funny constants like the universal gravitational constant. This is the model. But remember earlier we said, wait, this is centripetal force, and that's equal to mass times centripetal acceleration. So it turns out that v squared over r is the centripetal acceleration. So now let's go back and try to put everything together into a nice package for the model. I guess I was telling you more about centripetal acceleration, but now I'm waiting on me. Oh, there we go. Okay, so now we're back and we're going to talk about the model. So now centripetal force is equal to mass times centripetal acceleration. But we know that centripetal acceleration is v squared over r from all of the things we put together on the Pivot Interactives activity. The mass, m, is the mass of the object that's going in a circle, whatever that object is. The v is the speed, which is the tangential speed of the object going in a circle. And r is the radius of the circular motion. Okay? Remember that we are emphasizing that the speed stays constant in circular motion. In any of the circular motion that we will investigate, the speed stays constant. So now we're going to make a connection that you want to take notes on and that is pretty important. And that connection is between the gravitational force and this equation for centripetal force. And I'm just waiting on myself to get to that screen. Okay, so gravitational force is equal to centripetal force when the gravitational force is causing something to move in a circular orbit. We've seen that with the FET, where we saw a planet going around the sun. And the gravitational force is g m1 m2 over r squared, and the centripetal force is mv squared over r. So we're trying to see what's going on with this relationship. And it turns out mass 1 is the center mass, for example, like the sun. And mass 2 is the orbiting mass. In the example that we're using, it would be the Earth. So the Earth moving around the sun would be the orbiting mass. Okay. You could also think of mass 1 as the big mass and mass 2 as the little mass. That's also another way of thinking about it. So on the other side of the equation for centripetal force, that mass, that m, that's the mass of the object going in a circle. So it turns out that the mass of the object going in the circle is the same thing as the orbiting mass, or the same thing as the little mass. So since they're the same, and they're on opposite sides of the equation, we can cancel them out. So that mass drops out of the equation. And we're left with gm1, or mass of the center mass, or the big mass, however you want to describe that mass, whatever is winning, over r squared, and that equals v squared over r. Now it turns out that we have r's on both sides of the equation as well, and those r's represent the orbital radius, or the distance between the two masses, orbital radius, and since they represent the same quantity, we can also cancel one of them. So it turns out that big G times the mass of the big mass, or the center, over the orbital radius is equal to v squared. And we call that the orbital velocity, which is really an orbital speed, since we're not really talking about the direction. Okay, there's one more piece of information that I give you here for notes. And that is the idea of an orbital period. Period is the amount of time that an object takes to complete one cycle of its motion. Capital T is the symbol we use, so capital T is the period, or the time for one cycle of motion. In the case of an object orbiting or moving in a circular path, the period would be the time it takes for that object to go around the circle one time. And we want to see if we can figure out what the orbital period is. Okay, so the orbital velocity, we already figured out a way to figure that out above, but there's another way to figure that out. And that is just by figuring out the distance that the object travels in a circle divided by the time it takes to travel. And the distance that it travels is the circumference of the circle, or the circumference of its circular path, divided by the time, but the time is the period, so we're going to put capital T. And we calculate circumference of a circle as 2 pi times the orbital radius over the period. So we have that orbital speed is equal to 2 pi r over the orbital period. So that's another way of figuring out orbital velocity.